Good evening. I'm deeply honored and humbled to accept the José Leite Lopes thesis prize for my work on instabilities due to supra-thermal particles in fusion plasmas. I've been affiliated for the past 3.5 years with the Princeton Plasma Physics Lab, but today I'll be mostly talking about the work I did as a PhD student at the University of São Paulo from 2012 to 2017. And my supervisors were Professor Ricardo Galvão, from whom you just heard in the last talk, from São Paulo, Nikolai Gorilenko from Princeton, and Professor Herb Burke from the University of Texas at Austin. And this work received funding from the São Paulo Research Foundation, SAPESP, and the US Department of Energy. So let me unpack my title. I'll start by talking about what plasmas are and how fusion can be harnessed in a lab, and how supra-thermal particles are important to keep fusion reactions running, and the instability that eventually arise from their interactions with waves. So plasmas essentially are ionized gases that because they're charged, they respond in a very complex manner to applied electromagnetic fields, and they're the most abundant form of matter in the known universe. So in our daily lives, we usually see solids, liquids, and gases in this, which is the corner of parameter space in this temperature versus density diagram. And plasmas occur across a plethora of parameters, from aurora to the solar wind and to the center of the sun, up to the very hot temperatures needed for fusion to occur on Earth that I'll be talking about. So note that the center of the sun has a temperature which is 10 times lower than the temperatures needed for fusion in a lab. So in this presentation, I'll be mostly focusing in this type of system here. So how can we harness fusion energy on Earth? How can we replicate the reactions that happen in the interior of every star? So what I show in the bottom plot here is essentially the cross-section versus energy. And I have here 3 types of reactions: deuterium tritium, deuterium, and deuterium helium. And for the temperatures that are convenient in experiments, the one that maximizes the cross-section is deuterium tritium, which is this reaction I'm showing here. So if you have enough pressure in the system, then eventually you can induce overlap of the wave functions of both, and up to that point, the strong nuclear force kicks in, and eventually you have fusion, which releases an alpha particle, which is a nucleus of helium, and a neutron, both very energetic. And the neutron we cannot confine in a machine because it's not charged, but the helium, yes, we can, and we do want them to transfer part of their energy to the reacting plasma. The neutron we want eventually to be collected at the walls of a machine and eventually rotate a turbine and generate electricity from there. So the recipe to produce such reactions is essentially start with a 50-50% deuterium tritium mixture, heat to about 100 million degrees Celsius, confine it in a machine using magnetic fields, and keep supplying fuel as it burns. The second half of this presentation will essentially be concerned with the confinement of the alpha particles and how they excite instabilities in the plasmas. So why thermonuclear controlled fusion can potentially offer an alternative for a source of energy for the humankind? What advantages does it offer? So it's a very big scientific and technological challenge, but it does offer many advantages, such as it's intrinsically large scale. So the power plants would be of gigawatts order of power. It's intrinsically clean, so there is no CO2 emission and no long-lived radioactive waste. It's intrinsically safe in the sense that it does not rely on a chain reaction such as fission. So if something goes wrong with the machine, you can just stop the reactions and nothing keeps running after that. And it's virtually inexhaustible because you can basically extract deuterium from seawater, and you can breed tritium from lithium. So, okay, how to confine that plasma to offer an environment for fusion reactions? So there is actually a theorem that states that you cannot confine a plasma in a spherical geometry. You do need a toroidal topology as the simplest way of confining it. So imagine you have a field that goes around this toroidal direction. You have charged particles, so particles start following the field lines. But it's more complicated than that. Particles start to drift upwards because of a number of mechanisms, for example, density gradients or crossed electric and magnetic field. You're going to have this loss of confinement. So this toroidal field is not enough to confine the plasma because of the drift. And the ingenious solution is to combine, to actually, instead of considering this simple circular toroidal field, is to consider a helical toroidal field. So basically, particles keep following magnetic field lines. They have the cyclotron motion around them, but as they drift, the magnetic field lines take them up and down in such a way as to cancel out the drift. So essentially, the magnetic field configuration shorts the top and the bottom of the configuration, and that effectively cancels the drifts. So that's the type of confinement we're going to be looking at. So it's a superposition of the so-called toroidal field in this direction, the long way around the torus, and the poloidal field, which is the short way along the torus. The combination of them leads to a helical magnetic field. So this is a tokamak. So tokamak it's a Russian acronym for a toroidal camera with magnetic coils. And it's basically a confinement device that relies on such magnetic field topology. So in orange here, that's the plasma, the very hot gas that keeps spinning here. And you have a number of coils to confine that plasma and generate the field that is necessary for confinement. But in essence, we have in the central stack here, that's essentially the primary of a transformer, and the plasma acts as a secondary circuit of the transformer. So those circular coils, they generate a field along the white arrow here, and you have some correction coils, the vertical coils, that generate the field that leads to the helical direction. So far in the decades of research in fusion energy, many encouraging experimental results have been obtained with production of energy due to fusion. However, no ignited plasma has yet been produced. So no net fusion energy has been extracted from fusion experiments. So you do extract energy, but you need to input more to it. That's up to now because there is an experiment being put together in southern France called the International Thermonuclear Experimental Reactor, ITER, which means the way in Latin. So that's essentially a tokamak. In pink here, you see the plasma, and around it, you see a myriad of diagnostics and coils that are necessary to diagnose and produce such plasma. What you see here is the size of one person. So it's really, really big. And the targets of ITER are twofold. First is to prove the scientific viability of fusion as an energy source, not yet the commercial viability, but the scientific viability, and to collect the necessary data for subsequent machines, subsequent electricity producing fusion power plants. So ITER aims at producing 10 times more fusion power than it would be necessary to inject to produce the ignited plasma. So 500 megawatts from an input of 50 megawatts. And it's the most expensive single experiment ever. It will cost $25 billion, and it's being shared by, it's a joint venture between 6 countries and the European Union. This is how it looks like as of last month. More than 70% of it is built already, and the first plasma is expected to happen in 5 years from now. So this is the building that houses the tokamak. And this is the fisheye view of the whole ITER site. So you see that the tokamak is going to go inside here, and it's just a small fraction of the whole effort. There's a large number of paraphernalia surrounding it. And you see those big cranes as well. In Brazil, there are 2 tokamaks currently in operation, the TCABR at the University of São Paulo and the ETE at the National Institute for Space Research. Let me advertise that the TCABR right now is on track to undergo a major upgrade. This is basically the upgrade cartoon of what's going on. So in addition to all the ordinary coils that surround every tokamak plasma, it's being designed 2 sets of coils, the green one and the blue one here. So essentially those are called the correction field coils, and they will allow for unprecedented flexibility in the magnetic topology. So a cross section is shown here in black, and the plasma goes around the vessel here. This is the plasma, and those external coils are shown by those dots here, and they're going to allow for a lot of different shapes of the plasma. So TCABR will be able to access regimes which are not accessible in bigger machines. So, and I invite you to watch Professor Gustavo Canal's talk on this upgrade in 2 days from now. So there are still major scientific challenges for making magnetic fusion a reality. One of them is related to instabilities that propagate in the plasma. The other is how you keep high confinement modes and exhaust heat from the plasma. Another one is how you generate currents that do not rely on Faraday's law, so basically non-inductive currents that would allow for steady operation of the machine. What I'll be focusing in the rest of the presentation, and that's what my thesis work was about, is how to predict the character of those instabilities that propagate in the plasma. So most of those instabilities associated with supra-thermal particles, such as alpha particles, they are Alfvén waves. So Alfvén waves are the most fundamental type of oscillation in charged gases that are embedded in a region of background magnetic field. So Alfvén waves are nothing more than a result of the coupling between fluid equations and Maxwell's equations. So that leads to the so-called magnetohydrodynamic system of equations, which earned Hannes Alfvén the 1970 Nobel Prize. So those waves are mostly they mostly have to do with a background magnetic field, which is shown by B0 here. And if you have charged particles embedded there, then any displacement, any fluid displacement will lead to a restoring force, that in turn will generate an electric field, which will eventually generate a magnetic field across the background magnetic field. So the total field will be something like this. And those waves, they propagate along the background magnetic field. So the big problem with those waves is that they can strongly interact with the subpopulation of highly energetic particles, for example, the alpha particles, via a mechanism called the Landau damping that I'll show in the next slide. So that not only can seriously degrade the overall confinement of plasmas, but also can be a critical issue for the nominal operations of ITER. So what is the mechanism that allows particles to resonate with alpha N waves in plasmas? So that was first shown by Lev Landau in 1946. So essentially, think of a distribution function for the ions in a plasma. So that's how the distribution function changes with velocity. So you have a bulk of so-called thermal particles. So those are the most of the particles is here, like deuterium and tritium. However, you do have a minority of particles from fusion products, alpha particles, and also highly energetic beam ions that are injected to heat the plasma. So that generates this bump on the tail of the distribution function. And it so happens that the alpha N waves, they have a frequency and a wave number that allows them to live in this sub-region of velocity space here. So what that leads is that the alpha N waves satisfy a resonance at a region where the distribution function has a positive gradient, and that, as shown by Landau, that leads to a transfer of energy from particles to the wave. So what happens essentially is that the waves perturb the distribution of resonant particles in phase space, and it opens up an island, and particles interact with the mode in such island. And the final effect of that is you have a flattening of the distribution function around that resonance. So the net effect of Landau damping is originally you had more particles with energy greater than the resonant velocity here, with velocity greater than the resonant velocity, and those particles, as a result of the so-called phase mixing, they migrate to regions of lower velocity. And what happens is that the overall distribution of particles lose energy at the expense of the wave energy gaining, increasing in amplitude. So you have this interaction between particles and waves. Particles lose energy, that the energy goes to the wave. So what is shown here is essentially the energy of an electrostatic wave. You start with a very tiny amplitude, and because particles provide that free energy, the wave grows and eventually saturates. So that's what I'm calling instabilities, because a very big amplitude can lead to massive radial excursions of resonant particles and also the bulk particles, and that can degrade the confinement substantially. So when we look at alpha N waves in an experiment, usually they appear in two ways. They could either appear with a constant frequency, I'm calling here a quasi-steady frequency, which is this case here, but eventually they might bifurcate to a highly nonlinear scenario called chirping. So that's when the wave exhibits very rapid frequency variations, as you can see by those bursts here. And those two scenarios are very different when it comes to the losses of fast particles that are induced by those oscillations. In this quasi-steady frequency regime, the losses are dominated by diffusion, as opposed to in the chirping regime, in which the losses are dominated by convection. So in this case here of constant frequency, reduced models are applicable. You do not need to retain all the nonlinear features of the interaction, as opposed to chirping that the dynamics is intrinsically fully nonlinear and the simulations can be very costly. So a big open problem that the thesis has answered is what determines the likelihood of this scenario or this scenario. If you have certain plasma conditions, how do you know if the Alfvén wave will exhibit a constant frequency or a chirping frequency? So to answer that question, we resorted to basically an equation that gives, it's a result of perturbation theory. It's an equation for the evolution of the amplitude of the modes. So you see that the first two terms are linear. If you only have those first two terms, you have either exponential growth or decay. But you do have a nonlinear term, which is cubic in the mode amplitude A. So it's a complicated equation because it involves time delays in the arguments of the amplitudes. It's an integral differential equation and it's nonlinear. In the kernel of that equation, essentially have two parameters that have to do with the stochastic events experienced by the resonant particles and the coherent events experienced by the resonant particles. This equation can exhibit a very rich nonlinear scenario with many types of behavior, but there are two outstanding scenarios that are most common in the experiment. As I showed before, the constant frequency type and the chirping type. So this is perturbation theory of the full nonlinear kinetic equation. When that equation, the simulation of that equation leads to a steady saturation that's associated with a constant frequency. And when it blows up in a finite time, that signals that the perturbation theory is no longer valid, but it does hint us that a chirping response is likely to happen. So again, constant frequency, meaning this type of evolution in a spectrogram, and chirping being this type here. So what the thesis did was to generalize this theory to toroidal geometry, so basically for a tokamak. And that, after many frustrations and a lot of work, what we realized is that contrary to previous speculation from the community, collisions alone cannot explain the observation. So basically, when the stochastic and coherent events are only associated with collisions, it's impossible to make sense of the theory with experiments. And what we realized later was that turbulence can substantially increase the resonant particles stochasticity, so essentially this term here, and it is essential in determining the character of nonlinear evolution in experiments. So after the theory indicated this type of prediction, there were dedicated experiments in the D3D tokamak, which is the largest tokamak in the Americas. It's located in San Diego, California. And the prediction was that less turbulence leads to chirping. And what we saw is that, so in the upper panels here, what is plotted is the thermal ion heat conductivity, Chi, which is a proxy for the turbulent strength in the system. And what is plotted in the bottom is the spectrograms, as I showed before, frequency versus time of the Alfvén waves. And we were struck to see that the transition between a nearly constant frequency to a chirping response happens when the turbulent level has a marked reduction. So in all three cases, we see that the transition to this bursty, intense scenario happens near a minimum of the inferred turbulent activity. So in summary, I tried to make the case for why plasmas can be harnessed as a potential source of fusion energy and the advantages that it has. I mentioned that there are many challenges, many unsolved problems, including the one that I studied in my thesis, which has to do with control of instabilities and understanding of instabilities. So the main outcome of the work was an understanding at a more fundamental level of what experimental conditions change the character of alpha waves in experiments. When it chirps, when it has a constant frequency, and the underlying particle loss channel, if it's diffusive versus if it's convective. What we learned was that less turbulence, we learned that from the theory that less turbulence favors self-organized responses such as chirping, when you need to retain a lot of phase information of the resonant particles. And that theory was validated against the NSTX tokamak in Princeton and the D3D tokamak in San Diego, and further applied to ITER. And the ongoing research that this finding opened up is to try to understand and employ models, not only to predict the character of the nonlinear alphanic evolution, but also to go one step further and calculate the amount of supra-thermal particles being lost in experiments, and also to use external actuators such as waves or injection of particles to mitigate those instabilities. So with that, I conclude, and I thank you very much for your attention.